The significance of form, or the shape of the vault, is related to many things. Here I'm going to highlight 3 items. One is it will affect the visual impact of the shell structure of the vault itself. And I'll show you an example of the St. Louis Airport Terminal versus the Bacardi Rum Factory as an example of how the form will affect that visual impact. More important than anything else is safety, and I'll illustrate that through the example of the Tucker High School roof. And then finally, as I mentioned earlier, economy plays a major role, and I'll illustrate that with an example of the Montreal Stadium versus the Kingdome in Seattle. Going back to Anton Tedesko, one of his major designs was the St. Louis Airport Terminal. He designed this working with the architect Minoru Yamasaki. The architect's vision for this airport terminal, as you see here in the model, was a series of intersecting barrels. Where the barrels intersected at 90 degrees, these valleys formed in the vaults. This form of intersecting barrels is not the best form for a vault. And to the architect's dismay, Tedesko concluded that the vault needed ribs at the valleys and at the edges. This was essentially the wrong form for the vaulted design because it needed ribs. Visually, the ribs aren't so bad, but they conceal the thinness of the vault and make it look heavier than it actually is. I believe it would have looked more elegant without the ribs. But would it have been possible to design this type of vaulted structure without ribs? The answer to that question is both yes and no. If we use intersecting barrels as done here, the ribs were needed. But what if we used intersecting hyperbolic paraboloids instead of barrels? It's a different shape, the hyperbolic paraboloid, that has curvature in 2 directions and adds stiffness. And that is indeed what Félix Candela did. Félix Candela designed the Bacardi Rum Factory as a critique of the St. Louis Airport Terminal. By using the hyperbolic paraboloid geometric form, he was able to give the vault enough stiffness to eliminate the need for deep ribs and, in my opinion, arrive at a more elegant structure. We're going to learn more about Candela and his structures later on in this course. But visual impact is certainly not as important as safety. Safety is the most important consideration when choosing a form for your vault. The example of safety begins with a thin shell concrete structure designed by Anton Tedesko in Denver, USA. This is a hyperbolic paraboloid shell that was taken down in the 90s because the town wanted to build a high-rise building in its place. Another designer with less experience copied the general form of the Denver shell as a gymnasium for kids in Virginia. Tedesko said that the building should not be built because the shell was too flat and improperly reinforced. The shell was completed in 1963 and it collapsed in 1970. This was the roof of a gym of a school which was full of kids a bit earlier. Fortunately, the roof sagged noticeably before crashing to the ground, allowing people to leave, thus resulting in only minor injuries and no deaths. 3 other similar shells after this failure were observed to be flattening out. A fairly recent study indicates that creep was likely the culprit for this collapse. Creep is a phenomenon of concrete where the concrete, under constant compressive load, will continue to deform over time, and this is an important consideration for reinforced concrete thin shell roofs. In addition to visual appearance and safety, the form will significantly affect the cost of the vault. Let's compare the cost of 2 domes, one with proper form and one without. Neither of these were designed by Anton Tedesko. The King Dome was completed in 1976 with a span of approximately 660 feet, or approximately 201 meters. To generate the shape, the engineer, Jack Christensen, combined 40 triangular hyperbolic paraboloids. Unfortunately, the dome was torn down in the year 2000 to make way for 2 new stadiums. At the time that it was torn down, it was still in excellent condition. Let's compare the King Dome to the Montreal Stadium in Canada. The King Dome is a dome, as implied in its name, and if you take the cost of the King Dome and divide it by the number of seats in the dome, it comes to about $600 per seat. The Montreal Stadium structurally is a series of horizontal cantilevers. It does not behave like a dome. And if you take the cost of the stadium itself divided by the number of seats, it comes to $13,000 per seat. You'll note that the Montreal Stadium costs more than 20 times per seat compared to the Kingdom. Why is that? Let's start by examining the form. The Kingdom is a true dome that takes advantage of the 3D behavior of domes to reduce stresses. The Montreal Stadium is a series of horizontal cantilever beams, which is not so efficient for carrying loads. The Montreal Stadium is elliptical, meaning that every cantilever was different. Standardizing the pieces would have helped to reduce the cost. The Montreal Stadium included many unique pieces and details and didn't have the benefit like the Kingdom of having few standard pieces. Under a deadline to have the stadium completed in time for the Olympics, lots of equipment and people were brought onto site and the project was rushed, leading to costly mistakes, one of which was misalignment of ring sections. Tedesko commented on the Montreal Stadium in a World Congress on Structures in Montreal in 1976. He said this, quote, "My reaction is one of disappointment. I find the final product, the details, ill-conceived, ponderous, lacking in simplicity, lacking in grace, and without finesse. I believe that there was no capable, knowledgeable engineer experienced in construction, active from the very beginning to guide the architect. I suspect a lack of partnership, no early joint effort between designer and constructor. I feel, for instance, that the 600-foot span velodrome should have had more construction depth, in which case forces would have been smaller and details would have been less heavy. I would have preferred to make use of the three-dimensional action. I would like to have seen some advantage taken of dome action in the roof of the stadium, with resulting savings in materials and cost. I can think of men like Nervi, Esquillon, Finsterwalder, Candela. If any one of these men had been in during the early design stages of these structures would have been more elegant, proportions would have been better, costs would have been smaller." Tedesko mentioned Finsterwalder, the German who published the mathematical formulations for barrels. Although I didn't have time to discuss, Finsterwalder designed many structures, including bridges. Tedesko also mentioned Nervi and Candela. In my opinion, these two men surpassed Finsterwalder and Tedesko in expressing creative forms for reinforced concrete vaults. Who were these men and what did they design? Keep watching the lectures to find out. Next, we'll travel to Rome to study Pier Luigi Nervi.